if you want me to be. It's not officially a lecture. I don't even think it's being recorded for the echo. So I can really be off color here. If you want, you bastards. I love Americans. Kind of one. We're America's hat, is what they say. America visa system. Who's an American physicist? Yeah, we have an American biologist. Right? Yeah, I would rag on the physicists harder if we had an American physicist in here. Neither, I guess, would be my answer, because I'm Canadian. I don't have to spend any mental energy determining who I would vote for. It happens every 4 years that they do this. They say the whole world will collapse around America if you don't elect so-and-so. And then they all say they're moving to Canada, and none of them ever move to Canada. Huh? Keep the Americans out. They're nice people if you get out of the airport. The airport people are dicks. No, but I was at a Green Day concert, and they were like, oh, if Bush gets reelected, we're going to move to Canada. And I think Amy Schumer is going to move to Canada. And they always say they're going to move to Canada. No one ever moves to Canada. Because then you're living in Canada. And you're like, oh, this is crap. I want to go back to the U.S. Cold. We have no cultural identity. We're just like a loose group of immigrants. Nothing wrong with that. We're just not a country. Right? What does it mean to be Canadian? That's why I like Australia so much. You guys have like a national identity. Like going around and stirring shit all over the world. Did you see this thing about these two guys who pretended to be the Australian golf team? And they went to North Korea? Those guys are legends. Like, I was watching it on the project. I'm like, hey, could this seriously happen? Or you guys, who were the ones who were in Thailand or something with the underwear? Yeah. Yeah. Didn't they get, like, held by the police or something? I like this place. See, you guys go out and have fun. We're just too differential in Canada. We're just too busy saying sorry to everyone for everything. You can be in Canada and bump into someone, and that person will apologize to you. Like, it's just like this weird vocal fry that we have, that we're just constantly. It's not a stereotype, though. It is 100% true. Okay, any other questions about my nationality before we start on vector calculus? I know you may have never met a real Canadian in your life. Okay, so what did we learn this year, I guess, is the question. So now that we've sort of gone through everything, I just want to go through it all again in a couple hours. And I'll tell you what stuff that you should learn and what kind of stuff that you don't have to learn, right? Because very often we're able to reduce. So a lot of these lectures, I introduced one thing, and then we did like 3 versions of it. But you only really need to know the one thing, right? And how to convert everything into that one thing. So I'm going to show you the stuff that you need to learn and practice, so that you can all destroy the exam, right? Because I want to give you guys good marks. You have to give me correct answers in order for me to give you good marks. There's not a lot of flexibility on these multiple choice tests. So please be careful. Okay, so first let's discuss some notations. And just, this is informal, just shout or throw something at me. There's no echo, so again, we can be off color. Okay, so let's discuss some of the notations that we had for this course. We can have the length of a, am I louder than normal? Is this louder? I can hear my echo. It's like really off-putting. Can you still hear me? Yes? How about now? That's better. Okay. So here's our notation. So if I have a vector, and let's say that this vector is given by n plus 1 components like this. If I put these double brackets around here, this is equal to the length of the vector, right? So the square root of the sum of squares. Okay. So the textbook sometimes uses this notation, right? The single braces, but I don't like that because you can confuse that with absolute value. Yeah. Although if you take the square root of the sum of square of one thing, you do in fact get the absolute value. What else do we have? Well, stuff that I never actually explicitly, well, laid out, or I think it's more appropriate to say I didn't realize this till the very end. I think I could do a way better job teaching you guys if you gave me another chance at it, but you were my guinea pig course. Okay, so C, we've been using for curves all semester, and these can be curves in R2, so planar curves, or R3, which we called space curves. We had D, which we had used for simple regions in R2. And if you're wondering why we used E for volumes, maybe this list now explains why. And we're just going down the alphabet here. We use the capital S for surfaces in R3, and A for area. And if I forget anything, just let me know, and I can go back and add these things. Okay, so central to the study of this course were curves and surfaces. And simply, a curve is a set of points. In R2 or R3. Okay. And we can describe this set in a variety of ways, right? So the curve C can be given by a function. So its points are given by this collection. Right? This is what we call the graph. We can have planar curves. Right? That is, curves that are in the plane. And these can be given parametrically by a vector function R. Right, where R is a vector function which takes scalar and returns a vector. Or we can have space curves. Okay. And a space curve is given by a vector function R that takes a scalar and returns a point in space. So C is the collection of points given by this. So again, we have graphs, planar curves, space curves. So normally, we're going to convert everything into this, right? A lot of the work that we were doing was to reduce everything to the case where we do have a function. But as soon as you have a function f, you easily have a vector function r that you can use to generate it, right? So we're going to do everything just as vector functions. Okay, so we have curves, but we can also now have surfaces. What kind of surfaces can we have? Well, surface, like a curve, is also just a set of points. And we have similar sets, right? So you can have a graph, which is the set of points x, y, z, but z is normally given like this as a function. such that x and y is in some D, where this D is called the parameter space. Right, so this is S when we're given a function, but better is to give our functions, or is to give our surfaces as parametric surfaces, which look like this. So your surface will be given by this collection of points generated by a vector function R, such that uv is in some parameter space, right? Where R has to be a function which takes a tuple and returns to you a triple. So we have graphs, which aren't really that important, but parametric surfaces will be something important. All right, any questions so far, right? So far we have objects, curves, and surfaces, and both of these things are just collection of points. Okay, so that's preliminaries. That's just developing a manner of symbols and notation so that we can communicate and know what we're talking about. What have we been doing all year? Well, we've been concerned with taking integrals. And at least for my section of the test, I'm going to be mostly testing you on your ability to integrate. From your previous training, right, you should be comfortable doing single variable integration, right? That is, you should be able to evaluate this. Does anyone know what this is called? Oh, it is the fundamental, there you go, theorem of calculus. Okay? So why is this fundamental? Well, it says that if we can reduce any of our problems into a single integral over a region like this, that we have an algorithmic way of determining the integral. Right? We need to find big F so that the derivative of big F gives you small f. And this fundamental theorem of calculus says that we can take the difference of big F evaluated at B minus big F evaluated at A to determine the integral over the determined region. Right? So all of the stuff that we've been doing this semester is basically coming up with techniques to take higher dimensional integrals and reduce them to this form. Right? But the iterated form is included in this, right? Basically, we only ever know how to do an integral of one variable in one thing. Right? So that's why partial differentials come up in the first place, right? Because we need to say, well, forget everything else as a variable and just focus on one thing so we can integrate it. Okay, so that's single variable integration. I assume that you can do single variable integration and employ all of the tricks, right, that you've done up till now, right? So trig conversions, integration by parts, integration by substitution, table lookups. Although we won't give you any crazy table lookup on the exam. You guys get a crib sheet, yeah? Okay, so since single integrals are kind of uninteresting, right? That's what you've been learning for the past couple years. We're really interested in what happens when you start doing more than one integral, right? If you want to move to higher dimensions, right? So a double integral is written like this. We want to take the double integral over some region R of some function in two variables, VA, right? Where f is some scalar function. Okay. If R is a rectangle, right, like this, then this integral becomes C D A B xy dx dy, right? And the point is that we know how to evaluate this, right, by doing iterated integrals. Do this integral, and it eliminates what? What variable? If you take an integral with respect to x, what variable disappears? X. Yeah, so this eliminates x. So the thing that remains is a function of y, and then this whole thing eliminates y. Well, we could also do other types of regions that aren't just rectangular. Rectangular regions are the easiest regions that we can do. But so how else can I still do this? I have a double integral of a function like this, dx, dy. And the first thing I need to do is eliminate y, x. Right? So that means I can move here and say this goes from some function of y to another function of y, and this is fixed. Or I can take some function in x to another function in x over a fixed region, and do eliminate y first and then eliminate x. Okay, so these are these iterated integrals that we were talking about. So what happens when I take the integral with respect to x, and then I don't evaluate at a constant, but I evaluate at a function in y? Right? Well, that still eliminates x. Right? So x is eliminated. And then once x is eliminated, you do an integral with respect to y and evaluate it over a rectangular region, and then y disappears. Same thing happens here, right? If I take the integral with respect to y and then evaluate at a function in x, this eliminates y. Okay? And then once you eliminate y, you do a single variable integral with respect to x, and you get a scalar back. This is called the type 1 region. This is called the type 2 region. Remember when I spent 2 hours explaining that? I got to fill, right? But this is that 2-hour lecture in a nutshell. Right? I don't care about type 1 and type 2 regions, because permuting x and y it's just looking at the shape by tilting your head. It's the exact same integral. You're doing this. Right? The point is that you need to eliminate a variable as you move through, and the outside one must be fixed. Okay, so those are type 1 and type 2 regions, and all we need to do is finish off with Fubini. Does anyone remember what Fubini did? Exactly. Okay. We know that if you have the integral from a to b and c to d of a function f in x, y, dx, dy, that we can permute these two things as we permute these two things. In fact, equal to the integral from c to d, a to b of fx, y, dy, dx. Okay, so we can do iterated double integrals, right? By making sure that as we do the integrals from inside out, that we're eliminating one variable as we go, right? And again, the main difficulty here is just going to be setting up the bounds. Okay? I think one of the questions is to convert from a type 1 to type 2 and stuff like that. Yeah, so if you're on your studies focused mostly on setting up questions, right? There's not going to be a lot of stuff where you're actually going to have to integrate something to completion. And there's no physics. Okay, so what's next? Okay, next we learned how to do a change of variables. Right. Because in this whole discussion here, it was assumed that we were working in the XY coordinate system, right? That we were using Cartesian coordinates, rectangular coordinates, to codify the portions in space. Right, so what happens if we don't want to take an integral in the rectangular coordinate system? We want to use polar or spherical for some different type of reason. We need to be able to convert rectangular integrals into different types of integrals. Right, so in general, if you have a double integral over some region R, some function in x and y, dA, and I want to integrate over some other region, S, so that, whoops, it's one of your colleagues. Probably should turn that off when I'm lecturing. Some salacious stuff can come through. All the sex party is ready. Oh, shit. Now I lost my thought. Okay, let me move this down here. So if you have some region R, and you want to transform it, so we can have a transformation which takes you from one type of coordinate system to another coordinate system. And say we can take a pair in here, and we map it to what we're calling some function x, uv, and some function y. Sometimes you can put tildes under these things to designate that. This is called the transformation provided to one-to-one function. We also learned what the Jacobian of t was. Right? That's this thing is equal to the determinant, and you have to take the partial derivative of the first component against all of its free variables, so dx du, dx dv, and then you do the same thing with y, dx du, dy dv. Okay. So given that you want to take the double integral over this region R in the coordinate system given by dA, and you have a transformation T which has this property that the points of R are equal to the points generated by your transformation when you take uv in your domain, or your coordinate domain. And so you have a region R, a transformation T, and when you act that transformation on that region, you get S. Right? So that's the connection between R and S. So write it like this. Right? The first integral is equal to the double integral over the new region S. Take f, you evaluate that at your transformation like this, and you multiply by the Jacobian of your transformation, u dv. So this allows you to transform between any one system to any other system. But we're usually going from Cartesian into polar or rectangular or something like that. And so this is basically the one thing you need for change of variables. Okay. What you should write on your crib sheet are a few of these change of variables which are very common, like a polar double integral. Okay. You could work this out. I don't need to give you the polar double integral because you can just put in the transformation for conversion to polar and you'll get it out. But that's a waste of your time. Right? So let's remind ourselves we can have a transformation which takes a polar point, so a length, a angle, and a height angle. Oh no, that's spherical, not polar. That's polar. Okay, so you take a polar point, that's a length and a angle, and you want to map it into the Cartesian plane. We say this takes r theta and maps it to r cos theta, r sine theta. We know that the Jacobian of t, the absolute value of it, is equal to this derivative, or this determinant. Works out to r, which means the double integral over some region r equal to this integral over this region, so transform on r, f at r cos theta, r sine theta, r dr d theta. Okay? That's all you have to remember is this thing down here. Okay? If you want to do a double integral in polar, right? You're given something in Cartesian that is something that's typically given in x and y's. Just replace all the x's with r cos thetas, all the y's with r sine thetas. Don't forget to multiply by the Jacobian down here, this r, and that's how you do that. Right? And then this becomes just a regular rectangular integral. Okay, triple integrals. So it's sort of the same jazz as double integrals, right? So we have three etas like this. We have some function, three variables. I want to do dz, dy, dx. Okay. So let's work from the inside out. If the first thing we're taking integrals with respect to is z, what can the boundaries here be? And what else? It can be two things, right? If I take the integral of f with respect to z and then evaluate it at a function in x and y, that eliminates z's and replaces them with x and y's. So what's left down here is eliminates z. Okay? So now that we've eliminated z, we have a function in x and y. So what can I put here? We have a function in x and y, and I want to have x's only. Yeah? This eliminates y. And finally, we will eliminate z by evaluating at a fixed. So eliminates x. Okay, so this is all you need to know about a triple integral. That it has to be set up like this, right? That you somehow have to view the region that you're given so that it can be expressed. Well, this is sort of the analog of a type 1, type 2 region for 3D. We don't have any name for it because there's one type for every permutation of x, y, z, which would be 6 of them. But the point is you can use Fubini's here too, right? There are 6 other versions of this. Right? So when you're doing your triple integrals, the most difficult thing, again, is just going to be setting up these bounds. So you usually are integrating over some volume E. So you usually do something like triple integral over E, blah, blah, blah. But our E here has to look like something fixed, something with a variable, and then something with the remaining 2 variables. Right, but you could change it. You could remove x first, then z, then y, or again, any of the other five possibilities. But you have to choose one which increments like this, which eliminates one, and then the next one, and then the next one. Right, and then if you can do your single variable calculus, they're good. That's all I'm going to show you today is how to take these questions and reduce them to a question of single variable calculus. Okay, so what kind of triple integrals do we have? Well, we have rectangular triple integrals. Okay. That looks like this. So you have a triple integral, and we usually call a rectangular interval in 3D a box, right? Because you have straight and a depth. Yes. And we're doing changes in volume, and these typically look like something like this, like A, F, this is the easiest triple integral to do. But remember, we have other types of rectangular regions. We also have spherical and cylindrical. Does anyone know what the geometric interpretation of this triple integral is? So when we're doing a univariate integral, it's the area under the curve over a interval. Right? When we're doing a double integral, we're finding the volume under a surface over a planar region. Okay? With a triple integral, we're finding a hypervolume, right, underneath, or you have some sort of hypersurface that's underneath the cube, right, and we're calculating that hypervolume from the cube. And so you have to imagine going from the univariate one up to the volume, and then from a volume up to a hypervolume. And then, in fact, you can go indefinitely. So anyways, that's the geometric interpretation of these triple integrals. We also know how to do a change of variables. I can upload both what I'm writing here and what I'm reading off of here if you miss something or something. Or just scream at me to go back. All right, so we also want to do a change of variables for this. For a triple integral. Okay, so what do we need here? So we need to convert between two regions, right? So basically the question is this: if you're integrating over some region R of this function, right, over volumes, and I want to make an equivalent statement over S, right? What goes here? Well, I'll tell you. So let me move this down. We again need a transformation, and we need it to go from some coordinate system, I'll call it UVW, back into rectangular, because we know how to take rectangular integrals. And given that T is a one-to-one transformation, we know that the triple integral over R equal to the triple integral over S, and this time R is the collection of points generated by this transformation. This is the relationship between R and S. And what goes in here? Well, it's the function. You want to convert from XYZ into UVW. You want to multiply by the Jacobian of T. And then you want to go du, dv, dw. So this is generic change of variables in triple integrals, right, if you're given a transformation. Okay, but something that you should write on your crib sheet. We have specific versions of change of variables that we do often, right? Namely cylindrical, spherical. Do we have any other ones? No, at least cylindrical and spherical. Right, so here it is for spherical. If you have the transformation, which takes a spherical coordinate, so a length, an azimuthal angle, and the other angle. This maps you back into R3. The mapping is given by what? R theta phi. This maps into R sine theta cos theta. R sine phi cos theta. R cos phi. Do you remember what the Jacobian of this is? Or at least the absolute value of the Jacobian? I'll tell you. It's R squared sine phi. But since you didn't remember, this is a good candidate for writing it down on your crib sheet. Okay. So we have f is some function, scalar function, which takes a point from R3 and goes to R. And here we know that the triple integral over this rectangular region and these volumes is equal to the triple integral for S. Convert f to spherical, multiply by the Jacobian. And then dr, d theta, d phi, and this is a iterated triple integral, so you're off to the races. I'll just give you the explicit relationship here. We know that R is the set of points given by giving R theta phi to this transform, or R theta phi is taken from S. This is what I've been calling the transformation applied to S. So it's just important to understand that these are related via this. Okay? Okay, what else do we got? Cylindrical triple integral. Okay, so here we have to have a transformation which maps a cylindrical point, so that's a length, an angle, and a height given by a scalar, which takes R theta z to R cos theta, R sine theta, z. Okay, so if you want to do an integral where they give you a region R in Cartesian, and you want to go over this function dv, this is equivalent to taking the triple integral over the polar region S, f r cos theta. I should probably stay consistent in the way that I'm writing this. So f evaluated at t, r theta z, multiplied by the Jacobian, which in this case is r, dr d theta z, where again R is equal to the transformation on S. Okay, so you should definitely write down this on your crib sheet for both the double integrals and the triple integrals. Okay, so that was basically it for just expanding our notions of single variable integration to multiple integration. That is, okay, what happens if we're now allowed to iterate on these integrals? So now we have to start thinking of things as vectors, right? And then doing calculus on strict vector objects. And when we start doing this, we can ask totally different questions. Since we can give, there's a lot of other shapes there are a lot of shapes that can't be given by functions. So like a circle, is that a function? A circle technically isn't a function. And a function usually means that one of the unknown variables is linear, right? So like y equals x squared is a function, but y squared equals x squared is an equation. I wouldn't call that a function, right? So a circle so given that a circle isn't a function, so functions really don't categorize enough shapes, right, to be interesting. So that's why we prefer these parametric definitions, or just seeing curves and surfaces as collections of points, right? Because insisting that they're functions is a pretty big restriction. All right. So, anyways, one of the new integrals that we learned came about by first talking about arc length. So, arc length is simply the length given. Well, if you have a curve, right? And then you lay a rope along the curve, and then stretch out the rope and measure it. That's the arc length of a curve. And we can compute that, right? So, given that, we have a curve, right? So suppose we have r, which is a vector function which takes a scalar and returns a tuple. We can say that a curve is given by the collection of points generated by r when t is taken to be in some interval, right? And this is in R2. Then the arc length, or the length of c, equal to the integral from a to b of the length of r prime t. Actually, okay, that's pretty illegible. Let me try it again. Integral a to b of r prime t d t. Okay. So here's the first example I'm going to demonstrate that this is the only thing you need to remember, right? Because we also suppose the question was now, what is the length of y equals fx, right? Between say x is in here. If I only told you how to do the vector version, how would you get the answer to this? Yeah, and what's the parameterization of f? R. Giving me your answer in pirate. I'll give you a hint, right? Any function can always be parameterized like this. If x is the first position in the tuple, what's the second? Does that make sense? So what are the points that satisfy this? So remember that we had these graphs. The graph of y equals f of x was equal to all the points x, y, such that y is equal to f of x, which is simply all the points x, f of x, right? Which I can make equal to r of x, right? If I make r of x equal to this thing. Because this is really crucial, so I want to be able to explain this properly. Okay, don't copy any of this down. Let's just talk about a graph. Okay, so here, this is a parabola-ish. And a parabola is given by y equals f of x equals x squared. Okay, so I can choose points on here. So this is a curve given by c, right? So there's many representations of this curve, right? One of them is y equals x squared, right? Another one is a simple enumeration of its points, 0, 0, 1, 1, 2, 4. But you have to list them all, right? So that's kind of a non-starter. So, but that's the thing, a curve is just a collection of points, and it doesn't matter how we generate those collection of points, as long as those collection of points are generate an equal set, right? So how else can I generate this collection of points? Well, I can say take x and then just do x squared, such that, you know, x is a real number. Are you familiar with set? Maybe this is the problem. Have you never been shown sets? Like, do you know what this means? Oh, okay. Yeah, so this is the collection of points, x squared, such that x is in R. And so do you see that these two things will match? Okay, but I can also write this like this. X, f of x, such that x is in R. Still an equivalent set of points. Right? Well, now I can say, well, let R t equal t squared. Right? And I can generate that set like this. So if you're given that, like a function, you can trivially generate it. You can trivially convert that to a vector function, which isn't true for the circle, because this is x squared plus y squared equals 1, say, right? And now you don't have y linear. You don't have a linear variable. You don't have y equals something. Right? This is why we had to convert this to polar in order to get a representation of it. But the central issue here is that curves and surfaces are just collections of points. The way that we generate that collection of points is up to us. And in fact, some of the ways that we'll generate points have properties that make things way easier to do. Right? I can describe to you a disk way easier in polar than I can describe to you the disk in Cartesian, even though these things are all ultimately equivalent. And so there's this notion in mathematics, equivalency versus equality. So have you ever seen this? Yeah, so this is a symbol for equivalence in mathematics, which is weaker than equality. So I can say 13 o'clock is 1 o'clock. So 13 is equivalent to 1, but 13 isn't equal to 1. Right, so that's a little bit of a side remark. So let me get rid of this and this. So is that clear now? And so because that's what we're doing with these transformations, right? You need to find some sort of transformation function t, so that when you apply it to the points of one set, it turns it into a different set. And then the point of these transformations is that we know how to account for the changes as we're taking the integral. Where was I? Okay, so you have a parameterized curve R, and I told you how to take its length. We also came up with a separate equation for the length of a function, which I'm saying you don't need, right? Because you just take your function and convert it into a vector function and just use the vector function one, right? So let's finish this. So if I know that the length of C is given to this integral, and if I know in particular that R of t is equal to t f of t, then we know that R prime t is what? 1 f prime t, which means that that integral up there equal to the length of this vector, a to b 1 squared plus f prime t squared square root e t. Okay? But don't remember this. It's a waste of time, right? Because it's so easy to convert it into its vector form. And I almost regret developing any of these shortcuts, because I don't think they're shortcuts. It's a shortcut just to figure out one thing well and to be able to convert into that quickly. I'm pretty sure this is how I managed to eke out my grade in calculus. I did get an A+ in vector calculus, so I am somewhat qualified. Although I was failing until my final. Then I smoked the final, so. Okay, so that was, did I miss something here? Oh, no, I didn't. Okay, so that's the arc length. That's the length of a line. So don't confuse arc length now with line integral. All right, so remember what I was saying before. So if we have a univariate integral, right, you pick a region on X, and you find the area under that. We extended that one extra dimension, which says that, okay, you can pick a region in XY to find the volume that is underneath the surface over that region, right? But since now we're in R2, there are different types of shapes that we can draw. We're not restricted to only regions, areas in XY. We can choose lines, right? I can say, well, I don't want to know the volume over some region. I just want to know the volume, or in this case, the area over some line. Remember these curtains? Right? If you have so imagine that you're standing underneath some volume, and you walk around a bit, and you're just sort of making a curtain, right? Swinging a curtain around. Geez, if I try to draw this, it's going to be... Right, so suppose, oh boy, well, I have to do something like this. Yeah, it's not too bad, right? So this top thing up here would be some surface fxy, but restricted, right, to one part, one line. So when we take a line integral, what we're really asking for is what is the area that is occupied by this curtain, what I drew here, which is different than asking what is the length of this line. Totally different, right? So this is the area under F over some curve, which we were calling a curtain. Okay. So that is C is a curve given by some vector function R, those endpoints. I want to be able to compute this, right? So we have the line integral over the curve C over this surface F. Okay? And now we no longer have our tools. We no longer have our single variable calculus tools, right? This is an integral with one integral, but we're not integrating over something rectangular. Right? We're not doing something easy. So now I have to tell you how we convert this into at least an iterated integral where you can use single variable calculus, right, as I promised. Well, so if you want to do a line integral, you simply do this instead. Do this single integral over F, evaluate that at RT, then multiply by the length of R. Okay, not enough room. You multiply by the length of the derivative of R dt. And then this goes from A to B. And this is a single variable function, right? So here, in here was a function in x and y, but in here is a function in t. Only in t. Right? So it's a single variable function, and we know how to take fixed integrals over single variable functions, right? So we've converted some integral that we don't know how to do into an integral that we do know how to do. Okay, so we also learned what surface area was. Well, I guess most of you knew, but we learned how to calculate it. The surface area is like a line integral, like arc length, except we're going to ask for how much area is occupied by the surface of something. Right, you could talk about the volume that a basketball occupies, or you can talk about how much area is around the surface of that same basketball. Okay, so for surface area, we're going to be given a surface, S, and we're going to generate it by R, a vector function. The area, or surface area, given by S is equal to, by definition, the double integral over d of the length of this normal vector. If you want to know why, read the notes. Right? But you don't really need to know why. You just really need to know that this is how you compute it. Right? So again, this is enough. Right? But we also came up with a specific equation for when the surface is specifically given by a function. Right? So when S is given by a function, right, then R this. Right, for the same reason when we had this whole parabola discussion, right? You can trivially turn a function into a parametric version. Right? Pick an x and pick a y, and that's what z has to be. Okay, so when S is given by that function, and then R is given by this, and the area of that surface is instead given by this equation. This actually requires some working. It's not intuitively obvious, but you can do some working. Okay? So write it down, but no, really, my preference would really just be to learn how to do this and then convert into it. Right? But there are shortcuts, I guess, right? Pro users. I don't even think that I would have learned, that I had learned that when I was in uni. Okay. So like the difference between surface area, between arc length and a line integral, there's also a difference between a surface area and a surface integral. The surface integral well, first requires that you have a surface which is generated by some vector function r, as usual. That is the coordinate space. So the surface integral is defined to be this. So the double integral over this surface, x, y, z. So this, again, is hard to understand because all right, so when we had double integrals, the thing that we could put underneath the surface was either a region or a line. We move up one dimension, we can, you can't really visualize it, but again, I can say, well, if you have a hypersurface, a surface which takes x, y, z and returns to you a parameter, right? This is, you can't visualize this. But you can put everything that's one dimension smaller than it underneath. So if you have some hypervolume, you can ask, well, what is the hypervolume? What is the volume underneath this volume? And that was triple integrals. That's when we were integrating over E. We can also ask, what is the hypervolume that is above this line in space? Or we can ask, what's the hypervolume over this surface in space? So that's what a surface integral is. Who cares what the geometric interpretation is? Just memorize this, or write it down, in fact. Don't even memorize it. That if you're asked to take the surface integral over a function in x, y, and z over the surface S, then you just need to take the double integral over d of f, evaluated at uv, right, which just means that you have to do the change of variables in f. You multiply by the length of this normal, and you're good at the races. Okay? Just the double integral. Because the only variables in here are u and v. That's the nice thing about making something parametric. Right? If it's a surface, you only need two things, right, rather than three. Right? This is why most of what we taught you is basically useless, because when you start doing physics, they're going to be like, oh, we have no parameterization for this curve or this surface. You don't have to do all these crazy tricks to make it look like a surface. Okay, so I'm just going to write a reminder down here. A line integral is to arc length as surface integral surface area. Okay? Just be mindful that these two things have very similar names, but are very different calculation. You guys ever have to do these intelligence tests where they ask you 100 questions like this? Mountain is to valley as black is to purple. Okay, so what do we got now? So we can integrate over rectangular regions in 1, 2, or 3 dimensions. We can integrate over curves. We can integrate over regions. So how do we relate regions with curves? Well, one of the first observations was done by Green. And we have something called Green's theorem. Right? And Green's theorem relates surface integrals with line integrals. Specifically, we can have the line integral over the boundary of some region D, dx, q, dy, right, where p and q must be functions, real functions of x and y. And this is equal to the double integral over the region D, partial derivative of q with x, partial derivative of p with y, EA. And this is a double integral. You may have to do extra conversions on this to finish. Some caveats. The boundary of D has to be closed, which means we put a circle there. And the boundary of D has to have counterclockwise orientation. So I'm just going to draw a picture here. We have some type of curve like this. It has to have counterclockwise orientation. The inside and the boundary is D, and the outside is the boundary of D, which is a curve. So the point of Green's theorem is that it's not really like it doesn't work on everything, right? It's all contingent on being able to organize your integral into these pieces or these pieces. You may have to do something clever, right, to put it into the form of Green's theorem. Like for instance, if you're given this, it may not, you're not given q and p. You're given the derivative of q with respect to x, and you're given the derivative of p with respect to y. You sort of have to say, oh, I can make this q, and the derivative of q turns into this, and this can be the derivative of p. Right? So you have to become sort of astute at noticing something has a Green's theorem's form, right? And move back and forth. That's the best advice I can give you on that one. Right? This only comes with practice. So please do as much as those questions as possible. And note that you can use Green's theorem to do either. You can make a line integral that seems hard into an easy double integral, or you can take a double integral that seems hard and make it an easy line integral. Okay? But the point is it relates surface integrals with line integrals. It had a very interesting corollary. Corollary. And that is that the area of D equal to 1/2 line integral for x dy minus y dx. And I won't derive that, but we did. Right? But this is when I was talking about this special instrument called the planometer. Because I think it's pretty interesting that you can relate the boundary of a region with the area inside of it. So if you're ever asked to calculate the area of some irregular shape for which you know the boundary of, you do it like this. There is a vector form of Green's theorem. I'll just write it. So the vector form looks like this. somehow regret writing this. The vector form of Green's. Okay, speaking of vectors, everything that we've been doing so far has been dealing with scalar functions, basically. We also dealt with a totally new class of functions called vector fields. Well, let's highlight the difference, right? So we were normally dealing with things like R, a parametric curve, and these parametric curves usually took two things, a triple of things, a quartet of things, but in each case it was mapping it to R, to a scalar. Right? A vector field takes a vector and maps it to another vector, even if it's the singleton vector. Even if it's something like this. You'd still have to see f as returning a vector of one element, right, rather than returning a scalar. Right, so we're now no longer have this, but we have these vector fields, right? And these vector fields are pretty important to the study of fluid flow, gas dynamics, right? The physicists are uniquely interested in these vector fields, which is why we had to teach them to you. But they're interesting. Okay, so we had 2D vector fields, right, which took pairs to pairs, apples to apples. 3D vector fields, which take a 3D vector and returns a 3D vector. And then we had some operations that we defined. So we defined what a gradient was. So a gradient is this, which is a mapping from R2 to R2. And so who remembers what the gradient is? Well, if always creepy that there's this Air Force base here. I'll never get used to warships flying over my house. It's very unsettling. I live from Canada. We have like one gun, which is shared by Air Force and Navy. Okay, so if you have a function of two unknowns, this means the gradient of f is this, df by dx, df by dy. And if you have a function of three unknowns, then you just got to add one more down here, right? And the geometric interpretation of the gradient was interesting spelling. Gradient. If you imagined a surface as like a mountain range, and I put you on that mountain range, then the gradient at the point that you're standing at should be the direction of the hardest way to climb. Right? So if you're in front of a cliff, the gradient is straight up, super hard to climb. Right? If you're at the top, if you're at a peak, then the gradient should be downward in every direction. We didn't really do any optimization, but this is how you would find peaks and the locally maximum and locally minimum peaks and valleys of 3D functions. Okay, what else did we want to do? I can rewrite thing down here. Okay, so we learned how to do some integrals over vector fields. I don't think they really have any names. But if you want to take the integral, right, that is an infinite amount of, you want to add an infinite amount of contributions across the curve C through the vector field F, dr, right? So really, you have to become good at identifying stuff like this. Right? What do these three symbols mean? But again, just write it on your crib sheet. Because when you see this, you should just immediately convert it, right? So if you know that C has this representation, then the integral over that vector field f dot dr over the curve C is equal to the integral from A to B. Take f, you evaluate it at RT, which makes this a vector function in t only. You take the dot product with respect to the derivative of t, dt. Right, so what do we got here? We got, well, this takes f, which used to have x, y, and z, and replaces everything with t. Right? So that is a vector comprised of functions of t. You dot product it with a vector also comprised only of t to get a scalar function of only in t. And there we go. I've reduced it, as promised, to a single variable calculus question. Right, now you just have to take the take the integral of this function with respect to t and do the a to b thing. Right? That's really why I only care that you can move from here to here. I assume that you can do the rest of the work. Right? And I don't want to reward nor penalize you for stuff that, you know, should be second nature to you. Right? You could all do integrals in your sleep, right? At the grocery store. Okay, so that's how you do that. I think was that called the flux? No, something different. Okay, I don't know name. I forget what the name of this is. I think it may just be a line integral through a vector field, right? Okay. Let's keep going. Okay, so I just mentioned, so what other operations do we have through vector fields? Well, we have the curl, and we have the divergence. The curl of some vector field f is equal to the gradient, or sorry, the Laplace operator, cross product f. Right, where this Laplace operator equal to d by dx, d by dy, t by dz. Right? It's basically take the partial derivative in every direction in your coordinate system. Right? So you want the curl of f? Well, that's just the Laplace operator, cross product f. When we also learned that the curl of the gradient of f is 0. Div, the divergence of f equal to the Laplace operator dot product f. Right? So it's important to know that this comes out as a scalar, and this comes out as a vector. We also learned that the divergence of the curl of f is the 0 vector. No. All right, I'll take a water break. We're almost done. Well, this, and then I'll take your questions. Okay. And all the echo people are missing out. Screw those echo people. Because this is... Oh, wait, yellow. Nope, I'm being captured. Oh, no, this means pause. I have no control over this, so if this is echoed, good for the echo, and if not, screw you, echo. Yeah, I can upload it, What was I doing before I was so mercilessly interrupted by the front row? All right, so we did a line integral over a vector field, so I'm pretty sure that's what it's called. So now we can do a surface integral over a vector field. And a surface integral over a vector field actually has a special name. It's called flux. And the flux is a double integral over the some surface through the vector field dot ds. But again, I just need to show you how to convert this to a iterated integral. Right, so suppose that your surface S is given by R uv such that uv is in D, and that N is the unit normal on S. So if you're a disk, then you have the unit normal pointing up, perhaps. Then this is equal to the double integral over the same surface, F dot product, the normal ds. Right, so this computes something that's a vector into a scalar. Right, and now you have a surface integral over a scalar function, and we know how to do that already. Specifically, so it's not really that useful to memorize that one, but that's not quite yet something that you can take the integral of, so I suggest you learn this one. If you want to take the surface integral, or the flux rather, through F, that's equal to the double integral over D now, F evaluated at your R dot product this normal. And I think you can do that du dv. Well, okay, maybe I won't say that now. I'll say dA. Right, but as you see here, this is going to be a function in a scalar function of u and v. So I've converted it to a double integral, which you can do iterated integrals of. This required some work. So see the lecture notes for more details. Okay, so the very last two things that we learned, the second last was called Stokes' theorem. Right. Stokes' theorem allowed us to relate the line integral through the vector field F with the surface integral over the curl of that function. We proved that this is equal to the double integral over the surface S over the curl of F dot product, the normal. Doesn't have to be a unit. The normal through S, and again, this is scalar. S is given like this. Okay. And you use this like you would greens. Maybe they won't write the curl. Like they don't write a curl F. Maybe they'll just compute the curl of F. And you sort of have to imagine it's coming from somewhere. So if you see something, if your integrand looks like it could be the curl of something, keep that in mind. These things aren't going to be extremely obvious. They'll only be obvious once you get some practice in. Right? There's no, I wish I could give you a stricter set of rules for these things, but at least I've given you the critical path through the course material. Okay, so what's the very last thing that we need to learn, or review? Is divergence theorem. And the divergence theorem relates a surface, the boundary of some volume, through some vector field ds is equal to the triple integral over the volume E of the divergence of F. This is a triple integral. An iterated one, in fact. One more thing I'd like to show you. As soon as I see those pen stuff moving. Okay. Just going to open up my totally legal copy of the textbook. I have like 7 copies of this textbook because I started using this textbook when it was like in its 4th edition. So every year from that, I was given a new edition of the textbook. I think now we're finally in 10 and it's stabilized. Anyways, I don't feel bad for downloading this. Plus Stuart's dead. Okay, so this here is what, and the textbook's actually very good. Right? So if you can get a textbook, it's better than my writing. But this is what they consider to be the point of the course. Maybe this isn't big enough. There we go. So we basically have given just higher and higher dimensional, this is not something testable, it's just interesting, that we just gave different versions of the fundamental theorem of calculus for different environments. Right, so the first was the fundamental theorem of calculus for the simplest type of region. Right? What is the integral over this interval, real interval? Then there's a fundamental theorem for line integrals. Well, what is the integral over a line? Right? I don't have to be an interval anymore, but I still have to be a line. And there's the fundamental theorem for taking a line integral. So an integral over a curve through the gradient of f. Green's theorem is what relates the area of D to the boundary C. And it's also considered to be a version of the fundamental theorem of calculus. So the point is that on the left, you have an integral, and on the right, you have less integrals. Right? So the first one, we have a 1 integral and then no integrals. The second one, we have a line integral and then no integrals. For Green's theorem, we have a double integral is equal to a single integral, and then we can use the single integral stuff. Right? So this is the whole point of the course, is to keep pushing these integrals down a level so we can employ all the tools. Right? Look at Stokes' theorem, same thing. 2 integrals on the left, 1 on the right. And Divergence theorem, same thing. Right? So we've in fact said, okay, we can take a problem that is hard in 3 dimensions, we can take a problem that's in 3 dimensions and write an equivalent problem in 2, and then take that problem in 2 dimensions and write it as an equivalent one in 1 dimension, 2 dimensions, and then we can use all of single variable calculus to do those problems. Right? So this course really was about converting questions, right? Where all the calculus stuff is old stuff. And so become effective at converting between equivalent forms. Right? And if you can do that, you'll probably do pretty good on your exam. So that's the review session I had planned. I'll use the rest of the time to do questions, but if you want to leave, you can leave. If you want to meet for consultation or something, I come to the university infrequently, so if you want to meet with me, just send me an email the day before or something, and I'll come to campus. But if you show up at my office, you're going to have a bad way of trying to find me. But I encourage you to please come visit me so I can sort you guys out. It's a lot less time consuming for me to help you in person than it is to do 100 emails back and forth. And I really want you guys to do well, right? Because it reflects good on me. And the opposite is true as well, right? So help me out, guys. Okay, so that's that. Is there questions of any kind? Challenges, or I asked you guys to bring questions from the book if you wanted those. Even general questions like, do a line integral question, because I brought the textbook. You can choose questions if you want. Otherwise, just get the hell out of here now. I don't want to see you anymore. guys want to like do work, I'm totally fine just staying here for like another 40 minutes and walking around and helping you guys. Yeah, I don't care. I'll do your homework for you. Okay, I'll come get it. Okay. The right document camera. I want to send it to the right projector. Good thing I figured that out. 6. All right, so I'm breaking the cardinal rule of instruction. You're never supposed to attempt these things in front of an audience, because you will always fail. Even basic arithmetic, you will fail. So now that I've prompted you, or at least primed you guys for failure, I'll give this a try. But you guys can help me if I can't get it, so that's good. Okay, so evaluate the surface integral. Okay, so we want to do this. S, here's the function x z. S is the boundary of the region enclosed by the cylinder, and the planes x equals 0 and xy plus 9. Okay, so you have to be careful. Okay, so these are one of these things that get hard because the coordinate system has been rotated a bit. So we have a cylinder whose free variable is x, right? So I'm going to do this. I'm going to say this is the x-axis. This is y, and this is z. So we're going to have a radius of our cylinder of 5. Okay, we're permitted to start at x equals 0, and we can go from x equals 0 all the way to x equals 9 minus y. Yeah. So you need to imagine that you have a cylinder, right? It's cut on the bottom flat, right? So you can lay it down on the table, but then it's cut like this. Imagine you're a block of wood, cut it at the bottom, and cut it like this. That's what it's saying. So cut it by a plane, x equals 0, then cut it by another plane. I don't want to draw it. It'll take me too long, and it's not really worth it, right? Because I know I have my bounds on x, 0 through 9 minus y. And so now I just got to figure out how to represent the rest of the region. Well, the rest of the region is probably best represented by the cylindrical coordinate system. Right? After all, it's a cylinder. So how can I get this? So if this is S, then I can describe S as what? The collection of points. Okay. So I'm going to give radiuses, then angles, and then heights. But in this case, the height is x rather than z, right? Just by the virtue of how I've organized my coordinate system. So R can go from what? Well, 0 to 5. It's a surface, remember? So we need everything, not just the boundary. If it was just the boundary, that would be a curve. I need all the angles, Then, this was the tricky part, x is allowed to go from 0, 9 minus y. All right. So now what do we need to do? Well, now I need to write this integral, which is in Cartesian, which is not represented as a cylindrical shape. I have to rewrite the double integral as a double integral in cylindrical. So I got to go look for that again. I want to prove to you that I've given you enough information to do everything. No, I screwed up. Oh, this is the boundary of the region. I read the question. See? I got to read the question carefully. But so this is where I got stuck, right? I'm looking down. I wrote S, which we know means surface. But this is the volume that I've written. Okay, so. But the volume is easy to write. But we probably should use one of our theorems. So how can I convert the surface integral of something into something else? Because if I want to do this as a surface integral, I have to do three surfaces. The bottom of the cylinder, the boundaries of the cylinder is the next one, and then the top one. But we can do this. We can convert this into a triple integral. Maybe we have to use the divergence. I answered something similar to this a couple weeks ago, didn't I? Oh, this is from week 11. Okay. Okay. Yeah, this looks like it. Oh, I know my mistake. Okay. Right. I am dumb. Surface is what? What section was this taken from? Because usually you can take cues as to what they want you to do. I know I've done this before. That's why it's frustrating me. Well, again, this is the magic of doing math in front of. Well, at least you can see my thought process, right? I'm like, the S, we can more easily give the volume enclosed by S, and that's a lot easier to work with than the individual surfaces of F. So I want to convert this into an integral over a volume. But for that, we only have divergence theorem. And xz isn't a vector function. It's a normal function. Oh, that's boring. Well, if we want to do it that way, then what? Okay, so we have a cylinder. So how big can y get? 5. So x can go to 4. Because what? There's you have a normal here, you have these normals here, and you have there should be a way to do this easily. Aha. Yeah, you have to do it by. So there's this exact question is in the textbook. Well, okay, fairly exact. Focus or? I learned that I needed glasses. I got in an argument with the lecturer about focusing the overhead. Crazy. I'm like, no, can't you see that it's clearly blurry? I'm like, use glasses, perhaps. Okay, so there is no clever way of doing this. There's the cylinder, and they said, okay, there's the top one, the side one, and the bottom one. Planted individually 3 integrals. Calculated with the sum. Want to do it? You guys can help me? Okay, let's try again. Okay, so we have a shape that looks like this. Let's call, we have a surface whose normal is like this. Let's call that S0. We have a surface whose normal is coming off like this. Let's call that S1. And we have a surface whose normal coming out like this. Okay, so now we have to parameterize each of those surfaces. Why did I close the book? There we go. Okay. Call this S2. So, what is the boundary? What is the boundary of S0? Sorry, it's just a weirdly worded question. It's not the boundary of S. This whole thing is a volume E. Boundary of E is equal to the union of these surfaces. Okay. We need to turn these into sets of points. What is S2? Well, that is the set of points. Yeah, it's that way. 0 to 5. Oops. 0 to 2 pi. Yeah. At x equals 0. So S1 is then what? So S1, oh, and S2 has what normal? Unit down. But remember that our coordinate system here is this. Right, so down is this. Okay, so S1 is the surface of the cylinder. So, oh no, I just done this wrong again. Oh, no, that's okay. But this surface is going to be what? It has to be, R has to be 5. It can be at any angle, but the heights need to be S1 is what collection of points? R is 5. Theta can be anything. And our heights, oh, we've determined our height. Right, that's x such that x is in 0 to 9 minus pi. Theta in 0 to 2 pi. And then, but we also need the normal on that. And we're also going to need to what is S naught? This is the circle like this. S naught we have 9 minus y. Well, I can at least do the integral of the bottom one first, so I can do something properly. Tempted to start over again. But I did a question like this in there's one in the notes, almost exactly like this. x equals 0. This has a radius of 5. Normal. Mass is equal to I think it's better if you just let me think about this and then write you something. Again, it's seriously, like when you leave, I'll have the answer in a minute or so. It happens every time. Yeah, the setup. Yeah, that's the. Yeah, after the lecture, I did this question with another student with different numbers, but now I'm somehow okay. Now I'm. Okay, I am committed to trying to solve this. As long as you will allow me to think. Actually, look at all the work that I do before I come to class. All the preparation. I know, because I did one like this. Yeah, see? Huh? Except mine wasn't slanted. What did I do here?